mathematically. Let's recall the mathematical description of the oscillation. It's given by a harmonic function like this. Okay, x as a function of t equals to xm. Okay, we can use sine or cosine function, it doesn't matter. Sine omega t plus phi. Okay? So this is the oscillation to describe one point. Like here, if I'm talking about the oscillation of this particular bar, okay, it can describe the oscillation of this bar. Once we use this as a source to initiate some wave, okay, so every bar is in oscillation. So each of them can be described by simple harmonic motion equation. Okay. By the way, since I'm going to talk about the oscillation up and down, let me use y instead of x. Okay. So I'm going to talk about the oscillation up and down. So let me use y instead of x. So this is for one point. Now, for each point, you will have a different oscillation. All these oscillations are the subsequence of the first oscillation, right? So they are related to each other. In fact, they should all of them should share the same frequency, or the period, or the angular frequency. They are talking about the same thing. So all of them have the same frequency omega, the same as omega for the source, the oscillation of the source. But they may have, and if there is no energy loss, they also have the same maximum oscillation position or amplitude. Okay. But what's different is that they have different phase. Because you can see, at the same time, some point reach the highest point, some point reach the lowest point. Some point is at the equilibrium point, right? So they have different phase. If we organize this fact into one equation, this is the equation for one point. Now, if we have many points, so the function y should be a function of both position, x position, and t, time t, right? So this is a two-variable function to also describe wave. Okay, so t means the time, x means horizontal position. So if we give some time, like say t equals to 1 second, so it's kind of frozen wave for t equals to 1 second. And yx will describe the position for different. Okay, so x equals to, like say, 1 centimeter, x equals 2 centimeter, x equals 3 centimeter. They will have different y. So that's a function of those different positions. If we fix position x for a particular position, then it goes back to the oscillation equation. It describes, like say, for x equals to 10 centimeter, it describes the oscillation of this point, particular point. Or x equals to 20 centimeter, it describes the oscillation for that particular point. Okay, so this is kind of you ensemble all the oscillation equation together, which is one variable function. Now we have a two-variable function. Okay. Have you started to learn about the two-variable function? This in calculus? Not yet? Okay. So for two-variable function, you can also take the derivative, but then the derivative is called the partial derivative. You can take the derivative with respect to t, with respect to x. Okay, but now we are not going to talk about those things. We just need to think about the function itself, understand how does it, how it describes this wave motion. Okay, and it takes this form. Okay, if the oscillation to produce a wave is a simple harmonic function, it's like that, then the wave also takes a form of simple harmonic function, okay, sine or cosine. So, but here you have only one variable t here, and here you have k and t in this form. Okay. Now, let's look at the similar thing here. Of course, you can see here you have omega, the angular frequency. Here you also have the omega, the angular frequency for the wave. And we say that this is also the angular frequency for each of these oscillations. For the same wave, they share the same angular frequency. So when we talk about the angular frequency of the wave, it means that's the angular frequency for this oscillation, this oscillation, this oscillation, all of these oscillations. Ym, that's called the amplitude again, okay? So amplitude, Ym, same kind of meaning. And if there is no energy loss, okay, so all of them will reach the same amplitude as the initial oscillation. So like it's kind of to show that we have all the points, we have the same amplitude. Okay. So again, they are the same for the oscillation of the source and all the points along the wave. And okay, for the oscillation, once we know the omega, it can give you the, and then we can calculate the period and the frequency, right? Okay, they're actually talking about the same thing. Omega equals to 2 pi f equals to 2 pi over t. So for the oscillation, you can talk about the period and the frequency. And for the wave, you can also talk about the period and the frequency here. And similarly, when we talk about the period of the wave or the frequency of the wave, that means all these oscillations, all these points here, they share the same frequency, same the period. Okay. So wave is what we call the collective motion. When we talk about the wave, when we characterize a wave, we're talking about the common feature of all these points. Okay. The period of all these oscillations, the frequency of all these oscillations. But what's special for the wave is this quantity, k. Okay, this quantity, k doesn't have. This one doesn't have k for the oscillation of a single point. Okay. But before we talk about k, let's emphasize. To describe the oscillation, we call this, what do we call this? Phase. And similarly, we also call what inside of the sine function, whatever inside of the sine function, phase. This is the phase of the wave. Okay? And for the phase of the oscillation, it's a function of time t. So it basically says, if you have some object in the oscillation, it has different phase at different time. What do we mean by that? We mean that, okay, at a particular time, it's maybe in the valley. At another particular time, it's maybe in the peak. And then at later time in the valley, in the peak. Okay. Phase is basically talking about, is it in the valley, in the peak, or somewhere between or close to the valley? Okay, that's what we mean by phase. And for the wave, you can talk about phase, but it's a function of time t and x. So that means at the same time, at some point, different point will have different phase. So at the same time, some point are in the valley, right, for the wave. Some point are in the peak. So this is the phase of the wave. Okay, they're different for different points. Now, we have a positive side and a negative side. They are related to the direction of the wave. Okay. So if you have a positive side there, okay, negative side means the wave traveling to the positive direction of the x-axis. And the positive side means the wave traveling to negative direction. Okay. Please note that a negative side here means a positive wave. And positive side here means the negative wave. That's something you need to understand. Okay? Any question here?